Any questions, anybody from last time? All right, so we were talking about the dual problem, and so if I have a linear programming problem, which we start with calling that the primal problem, and I have the primal problem and then the dual problem. We came up with the dual problem, and the dual problem is given by this, right? The dual problem is given by W equals to B transpose Y subject to A transpose Y greater than or equal to C, Y, Ys are larger than or equal to C. Maybe I should write them down side by side one more time. So what's the primal problem? The primal problem, I have Z equals to C transpose X. Right, C1 up to Cn. And then what are the constraints for the primal problem? The constraints are A times X less than or equal to B, right? And X is larger or equal to 0. Those are the decision variables. And also, what would be the dual then? With the dual that we came up with was, the dual objective was what? Dual objective is the right-hand side of the functional constraints. So the right-hand side of the functional constraints is B. So you take the B transpose multiplied by the dual variable. And then what goes here, well, this is A transpose multiplied by Y greater than or equal to what comes on the right hand side of the functional constraints of the dual. Well, that's the coefficients of the objective of the primal. So this is C here, and then Y is larger or equal to 0 as well. Is everybody okay with this? Now remember how many variables did we take for the primal? For the primal we have n variables, right? I have n decision variables here, and how many constraints I have here? M functional constraints. And what are the numbers here? How many decision variables do I have here? In the dual, how many dual variables? And how many functional constraints here? Anybody? Well, the number of decision variables is the same as what? Number of functional constraints of the primal. So this would be M. And then how many functional constraints do I have in the dual problem? The number of functional constraints in the dual problem is the same as number of decision variables in the primal. So this would be N. Okay. This would be n. So let's look at some examples. Let's look at some examples here. Let's say I have this primal problem. So primal. The primal problem that I have here is maximize. By the way, in the dual problem, are you minimizing or maximizing? In the primal problem, you're maximizing, right? And then dual problem, you're minimizing, right? Okay, so maximizing, let's say z equals to, is anybody at the door? No. Z equals to negative 2x1 plus 3x2 plus x3, and then the functional constraints are x1 minus x2 plus x3 less than or equal to 10. 2x1 minus 3x2 minus x3 less than or equal to 10 as well. And I have 0x1 plus 6x2 plus 2x3 less than or equal to 10 as well. And of course you have the non-negativity constraints, x1, x2, x3 non-negative. Okay, so I want to write down the dual. I want to write down the dual for this problem. Okay, can someone tell me what are we doing here? Are we maximizing or minimizing? We are minimizing, right? But minimizing what? So what is W? How many dual variables do I have? How many dual variables? How many dual variables? Y1, Y2 up to what? I'm sorry? Yeah, but I mean in this problem, how many dual variables do I have? 3. I have 3 functional constraints of the primal. So Y1, Y2, Y3. And what would be the so I have Y1, Y2, and Y3. What would be the coefficients of these 3 variables in the objective? Where are the coefficients coming from? The coefficients coming from the primal what? The right hand side of the functional constraints of the primal, 10, 10, 10, they will be the coefficients. They will be the coefficients, right? So what we are looking at, what I'm saying is that if the right hand side here, those are the coefficients of the dual variables in the objective function. And then what are the constraints? Well, what will be the first constraint? So the constraints will be in terms of y1, y2, y3, and it will be larger than or equal to something, right? And the second one would be also in terms of y1, y2, y3, larger than or equal to something, y1, y2, y3, larger or equal to something. For the functional constraints of the dual, what are the right-hand sides? What are the right-hand sides of the functional constraints of the dual? Where are they coming from? Anybody? Where are the where are the right hand sides of the functional constraints of the dual problem coming from? The objective function of the primal, right? So this would be what? -2, 3, and 1, right? And then what are the coefficients? What are the coefficients? How do I know what are the coefficients? Remember, if the coefficient matrix for the primal is A, then the coefficient matrix for the dual is A transpose, right? What is the relationship between A and A transpose? The columns of A are the rows of A transpose, right? The columns of A are rows of A transpose. So what does it tell you? The column, if you look at the, what is the column of A in this problem? A being the coefficient of the primal. What is the first column of A? The first column of A is given by the coefficients of what? Coefficients of x1. The coefficients of x1 will become the first functional constraint of the dual. So you're going to have 1 times y1 plus 2 times y2 plus 0 times y3, okay? The second constraint would be negative y1. Thus, the coefficients of x2 will become -3 here and then plus 6. So those are the coefficients of x2. The coefficients of x3 are 1, -1, and 2. So that's how I write down the functional constraints. And of course, all the dual variables are non-negative as well. Everybody's okay? Later on, we are going to write the dual in the standard form as well. But right now, we are just going to keep it this way. Any questions, anybody, on this? How I did it? Let's do one more example. One more example. And hopefully you'll do it before I do. So this is let's say the primal. The primal, you are asked to maximize z equals to x1 plus 2x2, and then the constraints are negative 2x1 plus x2 less than or equal to negative 2. Let me turn off one of the lights here. That's bothering me a bit. Okay, so x2 is less than or equal to 4. X1 minus 2x2 less than or equal to negative 2 again. X1 less than or equal to 4. And of course, these are the functional constraints, and then the non-negativity constraints is this. Okay, dual. Okay, somebody tell me what's the dual objective? We know it's minimizing. What's the dual objective? What's the dual objective? Minus 2y1, yeah? 4y2. Very good. So these are the coefficients here. First of all, I know there are 4 dual variables because there are 4 functional constraints of the primal. And then the coefficients in the objective function are coming from the right hand sides of the functional constraints of the primal. And now, what are the constraints? So, what would be the first constraint? What would be the first constraint of the dual? So, in the dual, the first constraint would be what? In terms of, y1, y2, y3, y4, and it will be greater than or equal to, right? Greater than or equal to what? That's coming from, okay, how many functional constraints do I have, by the way? How many dual functional constraints? Same as the number of decision variables of the primal. So I know there are only two. There are only two functional constraints. And the right-hand sides are 1. That's the coefficient of x1 in the primal. And 2, that's the coefficient of x2 in the primal. Now, the coefficients are coming from where? Where are the coefficients coming from, David? So the first functional constraint, the coefficients will be coming from the coefficients of x1 in the primal. What are the coefficients of x1 in the primal? Well, the first one is what? -2. What's the second one? 0. What's the third one? 1. And the fourth one is also 1. Okay, and the next one would be the coefficients of x2. So I get 1, 1, -2, and 0. Right? So I can write down the dual problem, and then I have, of course, y1, y2, y3, y4 larger or equal to 0. Okay? Any questions, anybody? Any questions at all? Okay, I'm going to write down one more problem here, but I will let you do that on your own. So here is an example. Let's say I am maximizing. Let me call that primal. Let's say I am maximizing z, which is 2x1 plus 3x2 minus 5x3, x1 minus x2 is less than or equal to 5, minus x1 plus x3 less than or equal to 6, minus 2x1 plus x3 less than or equal to 2, minus x1 plus x2 less than or equal to 4. That's it. So these are the functional constraints, and then x1, x2, x3 all non-negative. What I want you to do is come up with the dual on your own, okay? Everybody understands how the dual is obtained. Okay, so let me know if you're done writing it down. And the next thing that I want to do is show you that the dual. So I have the primal problem, and then if I take the dual of the primal problem, I get another problem. But what's the dual of the dual? Is my question clear to you? I have a linear programming problem, which I'm calling the primal problem. I dualize that. I obtain the dual of that problem. I get another problem. Now I'm going to take the dual of the dual again. My question to you, what do you think I should be getting if I take the dual of the dual? Yeah, I should be getting back to the primal, and let's see why. Okay, if I take the dual of the dual, I would be getting the primal. Okay, are you guys done writing this problem down? Okay, so my proposition then here, proposition is that the dual of the dual is the primal. My language is a little bit informal, but I'm pretty sure you understand what I'm saying here. Okay, so what's the dual of the dual is dual. That's the dual of the dual is primal. That's what I'm claiming. So let's look at what's the dual. We're going to write down the matrix form. Okay, so what's the? Let's say I have the primal. Let's say I start with the primal, and let's say the primal is. I maximize Z equals to C transpose X, okay, and the constraints are AX less than or equal to B, right? And non-negativity constraint would be X larger than 0. So that's the primal. So now I'm going to dualize that. If I dualize that, what dual do I get? Let me use an arrow here. So I'm going to dualize that. So what's the dual? So what's the dual of this? The dual would be, right, minimize W. What is that? Minimize what in this case? B transpose. B is coming from the right hand side of the functional constraints of the primal, right? And then what are the constraints here? A, what? A transpose Y larger or equal to what? C. C is coming from the coefficients of the objective of the primal. And then Y, the dual variables are also non-negative. Okay, so here I'm not worried about how many dual and how many primal decision variables you have, but the assumption is what? As before, the setup is as before. If I have n functional constraints and decision variables in the primal, then I have the opposite for the dual. Okay, now I want to put the dual now in standard form. So let's put the dual in standard form. So if I put the dual, can someone write down the standard form of the dual? Can you write down the standard form of the dual? So what's the standard form of the dual? Okay, go ahead. Anyone? What is the standard form of the dual? Standard form means whatever the form of the primal is, right? Standard form means what? Standard form means the objective function needs to be maximized, and the constraints, all of the functional constraints are less than or equal to, right? So look at the dual problem. How would you standardize that? So what would be, if I want to put it in standard form? What would be my objective function? Now I'm going to be maximizing, right? Objective function would be what? If you're minimizing W, yeah, you'll be maximizing negative W, right? So this would be negative B transpose Y. And how would you make the constraints less than or equal to? How would you make the constraints less than or equal to? It's multiplied by negative A transpose Y less than or equal to negative C, right? And Y is the same as before. So this is the standard form of the dual problem. Now, one thing you have to keep in mind though here is that suppose that the optimal value let's say the optimal value of the third problem is negative 10. If negative 10 is the optimal value of the third problem, then what's the optimal value of the dual problem? What's the optimal value of the dual problem? It'll be positive 10, right? They are negative of each other, right? Positive 10 here. So if the optimal value here, optimal value is here is 10, then the optimal value here would be positive 10. Okay, now let's dualize the dual now. So if I dualize the dual now, that is, I'm going to dualize the third problem, what am I going to get? So I'm going to go here now the opposite direction here. So if I dualize that, what's going to happen to my objective function now? Maximum, minimum, right? I'm dualizing. So our way of dualizing was, if I have a maximum objective, then I'm minimizing. And then what am I going to minimize here? What am I going to minimize here? I'm going to minimize what function? Anybody? I'm not sure what symbol to use for the functional here. I used Z, W. What else can I use? Q. Okay, Q. What would be the objective here? You're dualizing the third problem, right? So, anybody, what should I get here? How many decision variables am I going to get? Yeah, you're going to get this guy as the coefficient, but how many decision variables would I have in Q? Would it be the same as a primal? Yeah, because how many functional constraints I have here? The functional constraints in the dual, number of functional constraints of the dual is the same as the number of decision of the primal. So when you are dualizing the dual, you're going to get again the n decision variables, right? So I'm going to denote them for now by x bar. Okay, I'm not going to call them x yet. So this is negative c transpose times x, right? This will be negative c transpose times. Let me call it x bar. I'm not going to call them x yet. Okay. Right. The right hand sides of the functional constraints will become the new coefficients for the objective function, and then what are the constraints? What are the constraints? Anybody? What are the constraints? X bar will be greater than something multiplied by x bar. So what goes with x bar? What's the coefficient matrix here? And then what's going to go on the right hand side here? Negative b, right? The coefficients of the objective of the problem you're dualizing, right? So what is the objective here? Negative b transpose, right? So you get negative b. Now what is the coefficient matrix? Remember, when you dualized, you had a here, then you have a transpose here, right? So whatever coefficient matrix you have, you take what? Transpose of that. So you take negative you take negative A transpose transpose, right? Anyone remembers what is the transpose of transpose? What is A? You have A. What is A transpose? How do you get A transpose from A? The rows of A will become columns of A transpose, right? Or the columns of A will become rows of A transpose, right? That's what you do. Now you're doing the opposite. If you do it one more time, aren't you going back to A? So A transpose transpose is in fact A. So this is this thing here is in fact just negative A. In fact, let me actually write that down in red. So maybe I'm just rewriting this as negative A times x bar greater than or equal to negative B, and then of course x bar is larger or equal to 0. So that's what I get if I dualize the dual. So dualize the dual. Now what's the relationship between the primal and the fourth problem that I got? What's the relationship? Are they the same? You think they're the same? How am I going from the fourth problem to the primal? How am I going to? Yeah, you just standardize it, right? Now, of course, you have to call, you have to change x bar by x, but does it matter what I'm calling the variables? It doesn't matter what I'm calling the variables, right? But I mean, you can see that how many decision variables I have in the fourth problem. When you dualize, how many decision variables you get? The number of dual variables is the same as number of functional constraints of the primal. And then that carries over to the third problem. In the third problem, the number of variables, the variables are still the dual variables, right? So the number of variables in the third problem is still the number of functional constraints of the primal. Now when you dualize that, then what's going to happen? The number of decision variables you get would be back to the number of decision variables of the primal. The number of functional constraints you get is the same as the number of functional constraints of the primal again. Is that okay? So all we are saying here is that the dual of the dual is the primal. Dual of the dual is the primal. Okay? All right, so let's write up a couple of things one more time. The primal versus the dual. The primal maximizing Z equals to C transpose X. Here, minimizing B transpose Y. Here the functional constraints are AX less than or equal to B. Non-negativity constraints are there. Here you are getting A transpose Y larger than B. Y is larger than 0. Okay. Let's write down a couple of things. Number one, the number of decision variables. Let me actually say it this way. And so here I have n. Here I have n decision variables, and here I have m decision variables, 2. Here I have M functional constraints. Here I have N functional constraints. 3. What's the coefficient matrix here? The coefficient matrix is A, and the coefficient matrix for the functional constraints is A transpose. For what is the objective? What is the objective coefficient? Objective coefficient vector. What is the objective coefficient vector? The objective coefficient vector is here C. Here C, and the objective coefficient vector here is B, right? Let's look at the problems again before you forget. So B is the objective coefficient vector for the dual. C is the objective coefficient vector for the primal. And in the primal, you are maximizing. Remember, in the let me call that 5. The objective is maximizing. Here it's minimizing. Right. Let me also write 1, 2, 3, 4, and 5. 6. What's the right-hand side of the functional constraints? The right-hand sides of the functional constraints would be B, and all the constraints are less than or equal to. And in the dual, the right-hand sides of the functional constraints is C, right? And all the constraints are larger than or equal to. Is everybody okay? So you need to know, you need to understand all this parts of the primal and the dual, the connections between the two. Okay? Any questions? Any questions at all? It is important to understand this before we move on. As we talk about more results, everybody has to be clear on these topics. Okay, so do you need more time to write them down? Okay. So now what I want to give you is a theorem that I'm going to call the weak duality theorem. Okay, and the name suggests that there is probably a strong duality theorem, but we're going to see that later. So what's the weak duality theorem? It says the following. Let's let Y be any dual feasible solution, X be any primal feasible solution. So what am I saying? I'm saying that if you look at the feasible region for the primal and the feasible region for the dual, I am picking X and Y in the feasible regions of the two problems, right? So X is a feasible solution for the primal and Y is a feasible solution for the dual. Then I could say the objective value of Z, which would be what? Which is C transpose X. The corresponding objective value of Z would be C transpose X. That's going to be less than the objective value of the dual. Okay? Remember, that was our goal, right? To begin with, when I was trying to come up with the dual problem, remember our motivation was we wanted to come up with upper bounds for the primal objective, right? So what is this telling us then? What this is telling us is that is the following. What this is telling us is that here is, let's say, the objective optimal value of the primal problem, Z star, and if I look at any Z value, any feasible value of the objective function Z, so Z happens at Z is C transpose X. So X is a feasible solution, so I can look at C transpose X. That's the feasible value of the objective function. And Z star is the maximum, right? Z star is the optimal value. It's the largest possible value of Z. Now, what we are saying is that if Y is a feasible solution, then B transpose Y is a feasible objective value of the dual, and we are saying that value is bigger than Z, right? Am I making sense? We are saying that value. So W is bigger than any. So in other words, you should think of it this way. Any feasible objective value of the dual, is bigger than any feasible objective value of the primal. Right? Well, that implies what? This should imply. In the dual problem, you're minimizing W, right? And you're minimizing W, and at some point you're going to get the optimal value of the dual problem, W star, I'm going to call that. And we haven't said that they should be equal, but we're going to see that they have to be equal. The objective optimal value of the dual must be the same as the optimal value of the primal. We're going to see that. But right now we have this picture with this weak duality theorem. And the right away we can make a corollary here. Right away we can say, let me say corollary means that it follows from the previous theorem. Corollary is let W star be the optimal value of the dual and Y star is the optimal solution. Oh, sorry. let me say B, sorry, B, the optimal solution of the dual. So what I'm saying is that y star is the optimal solution, and then when you evaluate w at y star, you get the optimal objective value for the dual. And similar notation for the primal. Let x star be the optimal solution of the primal, and z star is the optimal value of z. Okay, so then I could say that z, which is z, which is c transpose x, z star, which is c transpose x star, is less than or equal to b transpose y star, which is w star. So all I'm saying is that the objective value of the primal has to be less than the objective value of the dual, and which is clear from the previous theorem. Previous theorem says every feasible objective value of the dual is bigger than every feasible objective value of the primal. Well, that implies that w star, after all, what is w star? W star is, after all, a feasible value of the dual problem, dual objective, and z star is a feasible value of the primal objective function. So this weak duality theorem implies then the z star has to be smaller than w star. Am I making sense? So far this is called weak duality theorem because the stronger one will say that they are actually equal. Z star and w star are actually equal. So weak duality is only telling us that z star is smaller than w star. But we are going to get to the point where we can say they are actually the same. Let's see. So let's try to prove the weak duality theorem. If you just give me a minute. What's the proof? The proof is very easy. What's the proof that happens? All you have to do is actually look at the following thing. You look at y transpose multiplied with a times x. Look at this quantity. Does it make sense to write y transpose ax? Does it make sense to multiply them? And notice that of course a and x make sense because ax is the left hand side of the functional constraints of the primal. Is it okay to multiply a on the left by y transpose? Well, yes, because what is the size of y transpose? Y transpose would be 1 by what? Y transpose would be 1 by m. And what is a? A is m by n. So the number of columns of y transpose is the same as the number of rows of a, so I can multiply them. So this is valid. Now you're going to group them together in two different ways. One is I am going to think about this as a times x right here, and also I'm going to think about this as y transpose a times x. Which one is what? On the right hand side, what are you getting? What is a times x? I know that a times x is less than what? Do I know that a times x is less than b? Well, that's the primal problem, right? ax is less than b. So I got that. Now, can somebody tell me what this is? Y transpose a, what is that? Y transpose a, what is that? Notice that if I look at y transpose a, right, I can think of that as the following. The transpose of that and the transpose, right? If I take the transpose and the transpose, right, then I get back y transpose a, right? Notice that by putting transpose, I didn't change y transpose a. But then what do I have? I have A transpose Y transpose here, right? But what is A transpose Y? A transpose Y is exactly greater than, A transpose Y is greater than, remember A transpose Y is the left hand side of the functional constraints of the dual. So A transpose Y would be bigger than B, right? So I get B transpose. So I get B transpose right here. B transpose A, X, sorry. B transpose times X. So B transpose X, wait a minute. I said something wrong here. I'm sorry? Which ones? Yeah, no, the only mistake I made here is that it's not B, sorry. What's the right hand side of the dual functional constraints? The dual functional constraints, the right hand side is C transpose, C. And so I get C transpose, so this would be C, and that's what I wanted. Sorry. If you look at the dual problem, I also made a mistake here. Dual problem, this should have been a C, right? This should have been a C. Remember, the right side of the dual constraints should be the coefficients of the objective of the primal. So that should be a C. So now I know that this proof works, okay? So there is no mistake here. When you take the transpose of Y transpose A, that's the same as you take the product in the opposite order and you take the transpose. So you take A transpose Y. It's like taking the inverse of the product. When you take the inverse, you have, yeah. So when you take the transpose, you get that. Okay, so that's the proof of the weak duality theorem. Very easy to prove. But we are not done yet. We have to move from